Okay, so for today, we have to talk about functions. More like of like the basics of functions. So like just how they are recognized, in terms of their graphs, like what makes a function as opposed to other things. So let me just start by reminding you of a couple of things. So the idea, like the way, like the concept of function in computer mathematics is like very, very, very general. So kind of like the most general notion of a function is the most general idea or an idea is that a function is that a function consists like well maybe three things. I'll give you some examples of three things. So the first one is some sort of objects or values which you refer to as the input of the function. Okay, so the first one is some values that some objects quantities which you refer to as the input, which you refer to as the input. And then you have another set of objects quantities, which you call the output. Which you refer to as the output. And then the idea is that the function, what it does is assign what makes this, so you have certain things that you call input, you have certain things that you call the output, and then what the function does is give you like a way to assign to each input one of the outputs. So like what the function does, a function is an assignment. It's an assignment of a single output to each input. Or one output for each input. So I mean, it looks a little bit abstract, but I'll give you some examples right now. So here, just to kind of show you that the way it's used like very broad. So here's one way to think about a function, like one collection, like one input could be like a just for people. Okay, so I'll put my input for this first example. So like just imagine like I just choose four people on the street, like so this would be uh well, just put in some random names. I choose four people. Okay, so notice that my input is not even like numbers, right? Like it doesn't have to be, it can be basically anything, like anything that you can single out as an object can kind of qualify as an input. And the output could be, you know, the output could be the year in which the person, well, like the output is going to be numbers, okay? So like I'll put like numbers between 1900 and 2024. Okay, that's not, that seems like a very big stretch, but it's just to say, then my input, basically the assignment that I'm going to, so for example, what's in here, like, what would be in here, like, 900, 1900 could be here, 2000 could be here, 2010 could be here, etc. Like, there are a bunch of numbers that fit into the category. And then, the function itself, again, what it's supposed to do is to assign to, to each input one of the outputs. So the assignment could just be like, I'll assign to each person like the year in which they were born. So that can be the assignment. So the assignment is just like literally like just like giving like a value, like giving an output to each of the inputs. So the function, like the assignment itself, the function, like kind of think about it as a rule, which is more or less what a function is to each person, I'll assign to that person their year of birth, the date of birth. So each person assign the year in which they were born. So I could kind of put this year like just because presumably no one would be alive before 1900 like today. So maybe there's in Japan like one or two people in the world who like is still alive, like very old, but not like the majority. So to each person, I will assign the year in which they were born. So like the way in which this can be represented is that I would have here like again like the input, more like as a diagram, which is nicer. I'll put here the output, and then I'll put always. Okay, so for example, Alice and Bob could both have been born on year 2000, so I'll put 2000 into my list. Okay, so I'll put like an arrow going from the input to the output to indicate that that's a value that was assigned to them. And then, I'll put it like Emily, like, I don't know, 2010. Give that to her, and then that's. Yeah, 1990. And by the way, you can put a bunch of other numbers here, like, you could put if you want, you can put literally every number between 1900 and 2024 like here, if you like, you could put like, 2005, etc. Like the only requirement when you talk about function is that everyone in the input must be assigned somewhere. It doesn't matter if you kind of on this side have things that didn't get assigned at all. So it's not that every year, like to be put in the output, it's not that every year has to kind of be attached to a person. Like the way it kind of has like a directionality to it. So you only care about assigning values to the input. You don't care whether you exhausted all the possible values for the output, if that makes sense. So whether you include the ones that were assigned, that were not assigned, is kind of like more up to you in a sense. But that is kind of like the main idea so far. So, you have something that you call the input, and then you have something that you call the output. And like in this example, you can see, like here's another thing that could have been the as long as something has like a unique answer, you can think about it as possible output. So like assuming that you could ask for someone's favorite color and that's unambiguous, then the output could have been the favorite color of each person. Like again, assuming that everyone would give you just like one answer. What's not allowed is that you would give me, oh, my favorite color is blue and red. You can only give one answer, like, because otherwise the assignment would not be well defined. So what I cannot do, what is not allowed, can I put my eraser? There you are. So what is not allowed, well, which in this case is pretty clear, but maybe with the color is like a better like example, because like, yeah, with color, someone could say, well, sometimes people wouldn't make a decision when you ask them for their favorite color, so they will give you two answers, right? So that's kind of like a more normal like example. So let's actually put that here. So like the same people like as the input, favorite color. Okay, and so okay, so like again, I'll just put three colors here, like red, blue, green. So yeah, it's you can have like the design is it's fine for two people to share the same color, like that's okay. So two arrows can kind of like land on the same output value. That's fine. What is not fine is, for example, for something like this is what's not allowed. So you cannot give more than one answer when it comes to a function, and like let me just complete this like here. So if you have a diagram that looks like this definitely would not represent a function. So okay, so this diagram does represent. Let me go there. This diagram does represent a function, and this one does not. So this diagram does not represent a function, since you know Emily has to, since like input Emily has to output colors. Okay, represent function since Emily was assigned to outputs. Um, so that is like the main, like the definition of a function, right? You have something you call input, you have something that you call output, and then there's like a rule, you know, and like the rule can be very like imprecise, but the important thing is like however you define that, at the end of the process, like you know, everyone here just get receives one arrow to go somewhere at the input, output. There, nothing else can, you know, you cannot kind of from each value of the input, only one arrow can emanate. Like let's say, is that making sense? Um, okay, now, the only thing that I like about this example is just to show you that, like, when you talk about a function, like, in this perspective, like, the things, like, it's like, on which the function kind of like works with, they're not even numbers, right? Like you have colors, people, like, you know, it can really be collections of things, like, you know, and you can still kind of like refer to it as as a function, from a mathematician's perspective. But obviously, like, you know, for our context, the most interesting case is when both the input and the output are actual numbers, because then there's a lot of more things that you can do. And there are other ways to represent the functions. So what we care about is the case where, you know, so the input is a type of like number and the output is also like another number. But it's kind of good to have like an example that shows you that, you know, you can apply this in more generality where you're not even working with numbers. Um, so our goal is to work with functions. Goal. Our interest is to work with functions where both the input and the output are numbers, or both. So here's an example of that. And this kind of will allow me to start getting into the idea of the graph. So, one example could be like, my input would be, I'll just take the first four numbers, 1, 2, 3, 4. And the output 3, 4, 6, 8. And the rule will be like, for going the input to the output is that I'll assign to each number twice that, I'll double it. So the rule would be to just like multiply each number by 2. Okay, but okay, like, there's nothing particularly special about these four numbers for that rule. So what you end up doing, like, if you wanted to kind of work with more numbers at the same time, like you cannot just start listing each single number like, and put them all here, like, inside this oval. So what you do is just call the input X, right? You could call the input X, so I'll call this called X. Okay. And so the rule what's producing is, what the rule is telling me is that I'm doubling X, so from X I'm going to 2X, right? And the value for the output is just called Y in general. Okay, so this is typically called Y. So I'll put here 2X and Y equals 2X or 2X equals Y, right? And so once you see like the rule from that perspective, right? You kind of recognize that another way to represent that is, in terms of the XY plane, right? So what you can do, because this is precisely the equation of a line, right? Like of the sort that we have analyzed before. So what is happening in this situation is that you have this line, Y equals 2X. I'll just do like a couple. Okay, so for example, well, 1 was assigned 2, so if you want to see it in terms kind of like I said, the diagram, like that's kind of like these arrows. I just like rearranging them in a different way. And then 2 was assigned 4. But you see, like in the diagram, kind of you always go from input to output. So here's that input, which is also called the domain, by the way. It's the domain of the function. And then this is the output, which is called the range or the codomain. I won't. Usually the domain is kind of more important in this type of problem, but I'll just refer to this as like this is a more important thing to remember what the name for that is. So okay, well definitely like the line I didn't do too well here. It should have been like maybe it should have been here, but so -2, there's -1, let's say, and then just to finish this zero goes to zero, right? So like in terms of errors or something, you can really go. Okay. So that is one way to represent the function, right? And that representation is called the graph of the function. So when you have well, maybe before I do that, okay, so far so good. Any questions about this? So like the idea, when you have a function where both the input and the output are numbers, you can represent that always as a sort of picture on the XY plane. So let me write that down here. So So when you have, and this is like the main idea of how you work with functions, like, for the majority of the math course you'll ever take. So the main idea is that when you have a function. So the function, usually the way you refer to it is as f of x, or like, actually I'll call it y equals f of x. So again, like x is always referring to the input, and y will be always referring to the output. So when you have a function of that sort, the one way to represent it, you can represent it on the xy plane in terms of what's called the graph, in terms of the graph of the function. Graph of the function. So the idea of the graph is just that in general, like, in this case, the graph would have been designed. In general, the graph kind of looks like a curve on the plane. Like the typical functions that we will work with, the graph look like curve. Looks like a curve on the plane. And the idea of the graph is that, let's say, if this had been the value of x, if you had like a value for x, it was assigned a corresponding value, like the input was assigned a value that I'm calling f of x. And so the graph just consists of the point x comma f of x. So this is the point x comma f of x. So that is the graph. So it consists of all those points. It consists of the points. I can show you the geometry graph for a second. So let me actually do this for one of the most important, like, one of the most important functions we'll work with on this course, which is like the parabola. So let me see if I can do it here. Okay. So before showing you that with the algebra, put it here. So here's like a more complicated function, like I'll put f of x equals x squared. Okay, that is like after lines, in terms of like interesting functions or like interesting equations, like you can think about it as an equation or a function that doesn't make much of a difference here. Kind of in terms of like the next step after a line is like something like y equals x squared. Okay, so how can you think about it? Like first, again, like before thinking about it on the plane, what you can do is like say, okay, I'll just choose like a couple of points and see what they got assigned to. So 0 was assigned to, it gets assigned 0 squared, like the rule is, well, I'll put it like this. What 0 gets assigned is what I would call f of 0, because I'm replacing x with 0 here. But according to the rule, it's like square the number that you are giving me. So 0 squared just happens to be 0. Okay. So 0 got assigned 0. So like that's like not much I can do there. well, I mean, I can draw that point, which is 0, 0. Okay. I can look at it in white, but then I'll put the others in color. So 0 got assigned 0, 0. And then, like, for example, 1 is getting assigned f of 1. The rule for f of 1 is 1 squared, which 1 squared is just 1 because 1 times 1 is 1. So 1 gets assigned 1 here. So I have 1, 1. Then 2 gets assigned f of 2. F of 2 is 2 squared. 2 squared is 2 times 2, which is 4. So that's already a bit more interesting. 2 goes to 4. Okay, so it's somewhere in here. 2, 4. Okay, then I can do like include some negative values also just to. Okay, so -1 gets assigned f of -1. That is -1 squared. And just to remind you, that is -1 times -1. So minus minus becomes when you multiply the negative signs becomes a plus, so you just get +1. I'll just put the plus here to emphasize that. So here's -1. -1. And just to do that last one, it's -2, -2 squared, -3 times -2, and again, minus minus becomes a plus, and you get +4. And again, obviously, you don't have to write the plus in front of it. I'm just trying to make it kind of more like emphasis on that. Okay, so that is how like you kind of start with a table, and that is some of the values for that this function, like the assignments, how they work with, right? So 1 goes to 1, 2 goes to 4, 0 goes to 0, -1 goes to 1 actually, and -2 also goes to 4. And then you kind of do that for all the possible points that you can imagine. So like cannot keep doing that forever. So like let me show you how that looks like on GeoGebra. Okay, so what I'll put at point A, comma A squares. So that is like 1, 1, and then what I have is kind of this slider here. So you see, like that is what I'm getting by choosing different values. So in fact, I can kind of do this a little bit more clear by putting A, 0 and 0, square. So this is like here this represents my choice of a x. This corresponds this is the corresponding value for x, like the assignment. So these are the 2 points these are the values that are paired, like this one is being assigned this value, and that is the point on the plane that corresponds to this assignment. Okay. So that is how they're changing. And then like what you have to imagine is kind of like joining all these points that have been labeled A together. So you just imagine that you kind of like painted the point. So like as the point moves around, it just like kind of like starts painting like some road on the plane. And then the road is y equals x squared, or like let me just write it as f of x equals x squared. And that's what you get like the parabolas, right? So, and we'll talk about parabolas a lot more later in the course. So I'm not going to kind of spend a lot of time on it, but I'm just kind of showing you how the graph in this case would look like. So again, like this is the x value, this is the y value. Input is always horizontal, output is the vertical one. And then the point on the graph is kind of like the input followed by the output. Like so that is what you get in this case. You can do this for a lot of other functions, like there's nothing particularly special about this one. But that's how you end up getting the graph for this function. Okay. Does that make sense? So just like a few like more things to tell you about recognizing like a function in terms of this graph. Oh yeah, another once I have the graph, I can kind of do these arrows. If you want, like it, you don't have to like I find it kind of. And so then so in the line that I already deleted at this parabola, and when I draw something like this, you kind of get these curves. The point is that not every curve that you draw on the plane would represent the graph of function. So let me kind of clarify that, which is related to the vertical line test. But not every curve not every curve on the plane can represent um, the graph of a function. So let me draw first like a curve that doesn't work, and then I'll write explicitly the vertical line test. So, for example, if you have like something like a circle, right? What is the issue with the circle? Well, the thing is like if you have the circle here, when you take a value for x, right? Uh, or you want to assign this value to this x, but then also you would like to assign this value to x as well. If you thought about this as a potential graph. So the problem with this is that x is being assigned 2 points on the circle. Okay, this one and that one. And so it's kind of similar to like the example I did at the beginning of the class with the favorite color, where you answer two colors. You can only answer one color, or you can only give one assignment of to x. So this is being assigned 2 points or two values for the output, so it cannot be the graph of a function. So this x, or I mean, not just this one, like actually any on the circle except for these 2 points on the equator would be it's getting assigned to value. This is another graph of function. Function. Since since the value since x as shown on the picture would be assigned two possible values for y would be assigned two values for y. Is that making sense? Clear. So that's called the vertical line test. So that is what you usually refer to as a vertical line test, which says that if a function, sorry, if a curve intersects a vertical line in more than 2 points, in 2 points or more, then it cannot be the graph of a function. So what it tells me that if a curve on the plane, if a curve on the plane intersects a vertical line at, at 2 points or more, then it can represent the graph of a function. So just to kind of draw one thing that works and another one that doesn't. So something like this. Okay, this one fails, so this cannot be it's not, doesn't represent a function because, for example, if I draw this vertical line here, the purple line crosses the curve at this point and at that point. I only need one where it fails. So it doesn't matter that there are many others that you could draw. You only need to find a vertical line that kind of cuts the curve at more than one point. So this fails the test, so it's not a function. Or not the graph of a function, not a function. And then like, anything that it kind of, you can draw that doesn't like, doesn't have that property, yeah, you can think of it as representing the graph of a function. So something like this could be, like, in fact, it can be a little more interesting. As long as like no vertical lines cross it at more than one point, this is okay. So this one is okay, so it can represent the graph of a function. Now, that doesn't mean that there's like a particularly simple formula for it, right? If you were trying to find it, like that's not what I'm claiming. Is that I'm just saying like, in a hypothetical world, like, yeah, this is like fine. Okay, so there are only two more things that I need to remind you about functions before we just work out some problems. So the first one is, that when you have, if you think of the graph, like, as a curve, there are like two things, like you can kind of like shift it, like left, right, or up, down. And that's kind of like useful, like in general. So like kind of like they're like this shifting or translation property. So shifting, translating a function. How to shift the graph of a function. Okay, so the first one is, so the first operation is like adding a number to the output, so like adding a number adding to the number to the output. So by that I mean, let's say you have a function. And I'm going to add as a number to the values the function is taking. So I'm going to consider something like, I want to kind of move every value the function takes by a certain, like a constant amount. So like kind of like imagine like drawing a bunch of vertical lines. Oh, Right, they should kind of look about of the same size. I'm trying to kind of like, if you think about it like as a curve, I want to kind of move the entire curve up by the same amount. So like say if this is like 2 feet, like each point gets moved by 2 feet. It's like a constant shift, If you think about the curve as some sort of chain on the plane, it's just like like moving all of it vertically up. So like this is going to be the new curve. Is that because that's kind of like the operation that I'm doing? Sort of move kind of like an elevator, like everything gets moved up. And so what is the difference between, let's try to work it out, like what's going on. If you take a value x, right? If you take a value x, then this value was being sent to f of x, right? For the pink curve, actually let me do it in pink because that's the pink curve. X was being sent to f of x with the pink curve, right? But let's say if you call c the amount that you're shifting this up, okay? Then what that means is that on the new curve, right? On the new curve, what is like the value you got sent to? Like, see, like there's a difference of c here. So the new value you're being sent to is f of x plus c, basically. This would be x plus. Because you're just adding a constant amount to like the values the function takes. So that is a new function which you call g of x. Because it is a new graph, it has like a new rule. It's just like take the previous values and add like a constant amount to it. This would be g of x. So g of x, which is f of x plus c. What that does is like move the graph of f up by the amount c. Moves the graph of f. Up by the amount c. So for example, to make this a little bit more concrete, that's actually what we were doing with lines, although I didn't say it in those terms. Like in the case of lines, it's a bit more clear. Like here's some example. Like if you have like a line like y equals, f of x equals x, that is a line y equals x, which we already know. So what I'm saying is that if I say that g of x is, if I say that g of x is let's say x plus 1, what does that mean? It just means that I'm taking the graph of f of x and I move it upwards by 1, and that's why I end up with this. So there's like this constant amount of 1 that everything was translated. Okay, so that is one way how you could have thought about like this line equation y equals mx plus b. It's just the equation y equals mx plus, so move that by b. So that is one interpretation, or let's say with the parabola. Like for example, if I actually let's do it with a negative value just to kind of make hopefully this will also help a little bit understand what's going on. So I shouldn't restrict myself to. Oh, now, what happens if my function is like, x squared, uh, minus two, right? The fact, okay, so really here, you're not really moving it up, you're moving it down by 2 units, right? Because it's plus minus two, so everything gets shifted downwards by 2 units. So in this case, the way, qualitatively, let's, like, I'll put the arrows going downwards. So I'm now moving this, all of this by two downwards, so. So this would be the graph of y equals x squared minus two. Let's, like, here it's negative two, right? So, like, if it's a positive number, it goes up. If it's a negative number, it goes down, basically. And the last one, which is a little bit more confusing. Okay, so this is actually like, so what I did here is kind of like take, take the graph, move it up, down, depending on whether I'm adding a positive or negative number. The other way you can move a graph is kind of like left, right. Okay, so let's try to think about that one because it's like a bit, a bit trickier than this one. So the other operation is to move the graph to the left or to the right. So and those are like the two operations. Like we only care about moving the graph up, down, or left, right. Like, basically everything else is like, when you move on the plane, it's kind of like when you're walking on the, like, on a city, like to go anywhere in a city, you can go east, north, south, north, south, east, west. Like, so everything can be done like as a combination of, uh, north, south, east, west, motions. So the second operation is just to move the graph to the left or to the right. So okay, so I'll kind of explain, it's actually a bit easier to say what happens if you want to move all of it to the right. So I'll do that one first, and then like the other one kind of works in the same way as before. So, let me do a graph that is a little bit easier to work with. I don't want to do anything too complicated. Okay, so let's say this is like the original graph, y equals f of x. And for this one, I do need a lot more pictures. So to just kind of like understand what's going on here. So what I'm going to do is kind of like, you see, like, there's kind of like a peak here on the graph. If you think about it as a terrain, so I will move it so that the peak is aligned with the y-axis. So the top of the mountain happens now up precisely on the y-axis. So just imagine grabbing like the entire curve and moving it like a little bit, like shift it a little bit to like here. Yeah, so I'm going to move this like this. So I'll kind of do this. Okay, so I have made, and so that is like the shifted version of the graph, right? I'll call that g of x. So I have shifted the graph to the right, and I'm kind of making it like drawing it in a way that's kind of clear what's going on because I just moved the peak from here to here. Shifted to the right. By an amount c. Okay. So it's not super clear maybe what's going on until you draw both kind of on the same picture, which is what I'm about to do right now. So this is where it can get a bit messy. So let me see if I can do it in a way that's not too complicated. So so this was like the original. On the iPad it's way easier because you can just copy paste on the iPad with no stability. So this is like the original you know version. This is the new version. Yeah. So that is like the original with the shift. Okay, so what is happening here? Let's just try to understand like the value and well, let's say that actually like the peak is more like here. Like I kind of move this so that the peak is a little bit past the y-axis. That's fine. Like it's actually better to think about it as well. Yeah. Oh, and I'm saying that I kind of moved everything by an amount of c. So this is kind of how the graph was moved, if that makes sense. Okay. Is that making sense? That makes sense. Okay, so like hopefully the arrows work. So how can I think about the value? Okay, so g of x is here. This is g of x. That is the same as the value that I'm getting from the function here, like from the original function here. So okay. This is a complicated question. Like, if this like so I took everything and I moved it by to the right by c. So that means that if I'm calling x this point, right? What is this point it came from? Like, if what is I don't know if even the question is making sense. Like, so is this is actually with something else like next to it? Like what should I put here that would give me x on this side, if that makes sense? So, all right, let's make it with numbers first, like, we, you know, um, let's say this was one, right? And I'm shifting, I think it's make it easier if I make it with numbers first. Let's say I'm shifting everything by an amount of two. Just make it easy. So every point here is being moved to the so this C is two, right? So like that's the amount that I'm moving every point to the right by an amount of two, right? So if I choose one here, where does it come from? What is the value here that was moved? Negative one, right? Excellent. So yes, so if I move, yeah, sorry, it's like this is why I said this one is more confusing. If I take negative one and move it two units to the right, I land at two. Okay, sorry, I land at one. That's one. Like so the distance between these 2 points is two. So what should I put here if I'm going to shift it to C to land at X? What you did was subtract, right? So x minus c, because if I take x minus c and I move it to the right by an amount c, you land at x, basically. So what that means, yeah, sorry, this is like a bit confusing, but what that means is that g of x should be the value that the original function had at x minus c. So let me put it like this. So g of x is f of x minus c. And that is what translates, what that means is that if you have a graph that looks, if you have the functions which are related that's like this, then the graph of g is just the graph of f moved to the right by c. So the graph of g is Okay, yeah.
Why would it be that the pink one's x minus c and then x instead of the pink being x and then the yellow being x plus c?
That is perfectly equivalent to thinking about it in those terms. Like the important thing, yes, you could have called, like, I'm about to erase it. You could have called this x and this x plus c.
Okay,
That's totally fine. It's just that I want to kind of give the formula for the new function in terms of just x and, having like the input being called x. So I kind of want to find like a rule for the new function, right? So usually the way in which, like what I'm trying to say is that if you do it this way, which is fine, like what you're saying is that, the new function, like the value that the new function takes is kind of like the value that the old function took, like c units far into the past, like, far, like.
right,
So the thing is that, if you want to think about it, when you write like a function, like what I'm trying to say is like when you write like a function, you write something like f of x equals x squared, right? You never write something like f of x minus 3, equals something. Like the function is, like the usual convention for writing the function is f of x. So
Okay.
when I want to kind of like refer to this new function, I want to say what is the value that it takes at x, and the rule is like, oh, just go c units into the into the path. Is that making sense?
yeah.
But yeah, it is easier kind of like in a sense to think about it, oh, you're going from x to x plus c. But we're kind of like reading it in reverse. That's why I kind of like did the arrows like in some like that. But and the rule is like for the new function, you want to kind of define it at x. So the rule is like, oh, just go to x minus c. But it is
Okay.
kind of like equivalent. It's kind of like saying, like it's kind of like this motion is relative type thing where like, if um like if I'm moving towards the door, you could be saying, oh, that I'm moving to your right, right? But I could also be saying that you're moving to my left. Like, from my perspective, like, you can think it's kind of like what happens, that is what happens on a train, right? Where like you see kind of like the train starts moving. And then if you look on the windows, you kind of see like the bit, like the little cute towns like going to your left, right? Like, so it's kind of like that same perspective where it's like, from the town's perspective, you're kind of like moving like to the north. But from someone on the train, you're moving to like, those things are moving to the south. Of course, like you don't really think that the other stuff is moving, you kind of think that you're the one that's moving, but I'm just saying like from like that perspective, it's kind of like, in a sense equivalent, like, if that makes sense. So that is kind of like this idea that motion is relative, but yeah, it's just that usually when you write a function, you kind of do want to refer to it as a formula for x, that's why.
How do you like differentiate like whether it's going left or up and down?
Okay, so let's actually do it for all the cases so that it's kind of, I'll do it for the parabola, okay? So. So what differentiates it is whether you are subtracting, kind of like the value that the function takes versus like, it's whether you're subtracting or adding to the input. So let me kind of explain this a bit better. So let's say the original function is f of x, right? Equals x squared. So this will be the original function, right? Okay, so which I said, look like this, right? If you kind of like move it up, if you move it up by 1 unit, right, which is kind of like what we had done similar before, then this one would be, you're moving this. What you're moving by 1 unit is the y values, okay? So y is what's changing by 1 unit, so that you just add the number 1 to the function, to the formula of the function. So if you add a number to the formula, that is like, what moves up or down the function. So let me put it like this, So like you see, like the number is being added to the formula itself, like to the equation, if you like. So this is like adding to the equation. This moves it up or down. Well, in this case, moves it up, right? But, okay, so what am I trying to say here? Let's compare it to like the shift to the right. If you take this one. And let's say I translated I translated the parabola to the right by 1 unit. Right? So now the x values are the ones that were shifted. And so the idea is that because of what I was saying earlier, this is just like x minus 1 squared. So you see, like the difference is now that I don't know why this always slides it today so much. The difference is that this one. The difference here is that the value was being is subtracted from from that variable itself, like from x. Whereas here, you don't you kind of don't do anything to the variable, you leave it alone. What you just do is like kind of like add or subtract the number to the actual function. But here, like what you actually do is change that you kind of affect the value for x, like you kind of you subtract directly from x. So here, in this case, like when you shift to the right or to the left, is x the one that gets subtracted or added? Let me actually, I'll do it like in a second with like algebra. You subtract. To the variable itself, to the variable. Not the formula. Not the formula. That makes sense. So let me put it, let me do it here because it's actually useful. Just to avoid all the classes. Like, let's do something that's actually more complicated, like x cubed plus x squared. Okay, that's how this graph looks like. Okay, so if I wanted to kind of move the entire graph north, like like I want to move it like 2 units north, then I just add 2 to the entire formula. Okay, so I'll call that g of x. G of x is going to be x cubed plus x squared plus 2. Okay, and that gives me like hopefully kind of like plausible, right? Like everything was moved by 2 up. Okay, so you see like it's like an overall 2 in the formula. So like you take like the original formula and you just add plus 2. But if I wanted to shift like the green graph, let's say 3 units to the right, every time you see an x, you have to replace it with x minus 3. So like the x gets replaced with x minus 3 in the formula. So how does that look like? It looks like x minus 3 cubed plus x minus 3 squared. Okay. And you see there that the green one was moved 3 units. But what I did is like let's ignore this one because I'm kind of doing it with reference to the original one, which is like the green one. So what I did, if you look at this, is like every time I see an x, I replace it with x minus 3. But I don't touch the formula elsewhere. That's what it is.
Wouldn't it have been the same if you did h parentheses x minus 3?
If I had done
If you did the minus 3 ahead of the h, like with it.
Oh, like here, you mean?
Yeah,
Well, the thing is like, that's also related to the question like that we were discussing before, like, the H is just like the name for the new function, right? Like the convention is always to write it like H of X minus, like H of, like the new function is always H of X or function of X. What you could have done, like what you could have said, like maybe that's what you're saying, is that you could have written, like, let me call it K. Like I could have done like on the algebra f of x minus 3. That you can say, and that will give you the same as like the translated graph, but like it's kind of like coincides with the red one because they're exactly the same formula. But what you cannot, what I'm trying to say is that you don't write this as h of x minus 3, because when you define a new formula, so a new function is always f of x or g of x or h of x. You can only see x there. But in terms of like the actual expression, the way you obtain it is by taking the original formula and doing kind of like a substitute, like replacement of x with x minus 3, whatever. And so, but yeah, like in terms of like the graph, what you kind of have to, like, so for example, let me erase it. So for example, when like it's like a shift to the north or south, it's just like kind of like a +2 or a +1, like it only has to be affected once, like the formula. If here like there were like two instances involving x, every instance of x has to be replaced with x minus 3. So it would not have been correct. What I'm trying to say, this would have been wrong. Like if you had just put if you had only changed one of them with x minus 3 and not the other, that's totally wrong. Like both have to be replaced. Every time you would see the x, it would need to be replaced with x minus 3 for this to work. Actually, what is this? What does it look like? Like it looks completely different, you see? So it has to be, I mean, like, if you ever take a program like computer science class or like programming class, like it's kind of like very much like linguist, like a language thing, because it's kind of like every single time you see the symbol x, you kind of substitute or replace it with x minus 3. But so in practice, like that's how you would recognize the effect on the form from the level of the formulas. Is that making sense? Okay, so that's kind of what I have to tell you for today. Let me give you the quiz and then I'll just give you some brief quick problems. So